Okay, so yeah, we're actually pretty good on lecture pacing. Um, I started on the recorded lecture last week talking about method of images, and this is really how you um, typically are going to cook up your Green's function solution on a bounded domain. We just had to sort of do something different on an unbounded domain because there's no hope in sort of, reflecting around boundaries. There's no boundaries to reflect outside of, right? But the idea of method of images, hopefully you watch the video, right, is that if you're in some domain U, right, that has some boundary, and you call the points on that boundary Y, okay, you'd really like essentially um, to be able to take your fundamental solution. So this is the idea of cooking up a Green's function, is you take your fundamental solution, right? But the problem is when you run into this finite boundary, it's going to have non-zero values on the boundary, okay? So the approach is then to say, well, I know that if I subtract off the fundamental solution itself, right? Because fundamental solutions are usually, rotationally symmetric and everything like that. But one that's reflected over here outside of the domain, then this will have the same value, okay, centered right here, the same value right here at the intersection point at the boundary. So this accomplishes two things. One, it puts the singularity of the additional term that you're using to cook up your Green's function outside of the bounded domain. That's good because you really only want one singularity on the inside. You don't want a bunch of additional singularities floating around. The other thing is you can sort of match the value of the function if you do this reflection uh, correctly or wisely. And so, in the case of this is the case that I talked through um, on the correlated lecture, right? This is like the idea of a half um, space Rn, right? So essentially, it's just reflection. I know that if I reflect over here, then the even symmetry of my fundamental solution is going to assure that I have matching values of my sort of boundary canceling function, that thing that we were calling little phi x y, um, and so that's the approach, right? So the reflection in the case of the half space Rn is relatively straightforward. That's the case that I went through in the recorded video. I want to unpack a little bit more today another case, which is that of the unit ball. And as you'd imagine, right, once domains start to be very peculiarly shaped, right, there's not going to be a nice, happy, conformal mapping between this space and the complement to this space that's going to work out, right? However, doing something like constructing a Green's function for a particular domain is a one-time thing, right? If you have the computational power to do it, there are ways to do it even for peculiar looking domains. You do that once, right? And then you can solve many different boundary value problems using that, right? So just because you can't get a nice clean Green's function by hand doesn't mean that this approach is not also incredibly useful when you have, more peculiar shaped domains. Okay, so we take, of course, the nice, uh, you know, platonic sort of examples here, unit ball, right? Because we can get a conformal mapping that works well for the boundary canceling. Okay. So the unit ball. What's the unit ball? We've um, met this object many a time. So we have a domain, right, that is just centered at the origin and then has some radius 1, okay? And the question really is, right, if I have this as my domain here, right, the open bounded interval here, right, how to map to the following domain, okay? Which essentially is going to be Rn with the closure of U removed from it, okay? What am I talking about here? Well, remember, in the case of the half space Rn here, okay, we took every point that lived in here and we just reflected it across the hyperplane that comprises the boundary here, right? And so every point in here could be identified with a point outside of here, okay? We want to do the same thing in this case, right? But it's not so clean as a simple reflection, right? But we don't want any redundancies, right? We want this sort of one-to-one mapping, right? And so maybe this is sort of a little bit of a complex analysis type problem, okay? But we're just going to kind of jump to the answer here, okay? So the question is, how do we define x tilde such that we're not in the closure of U, okay? Essentially given x, which is in the open and bounded domain U, okay? So the idea is to define x tilde as x divided by the magnitude of x squared, okay? So essentially, what happens in this case is that if I have my x here, right, the norm of this vector here, right, is always going to be less than 1, right? So dividing by its norm once is going to put me at the boundary. Dividing by its norm again is going to push me outside of the boundary, okay? And it's going to project me somewhere over to here. This is my x tilde now, okay? Now, as far as canceling out things at the boundary, you could imagine that, well, if I want to do that, right, I'm no longer going to be equidistant from the boundary from x tilde versus x, right? So I need to account for that somehow in the way that I scale the argument of the fundamental solution, okay? So there's sort of a second piece of cooking up the Green's function in this case, which is that coefficient that I talked about in the case of the half space is really going to come into play in this case. Okay. All right. So let's go ahead with this. So the Green's function for our Laplacian, okay, on this bounded domain, okay, is going to be defined in the following way. G of xy is equal to phi of x minus y. That's just our nice fundamental solution. Minus, okay, x tilde now minus y, okay, but we need to scale again by the magnitude of x, okay, because essentially the farther we push this argument out, right, we need to essentially sort of bring the whole argument of the fundamental solution back so that you're the correct distance from the boundary, okay? So that's sort of hard to imagine in your head. So let me just show how the algebra works out in this case, okay? First of all, right, note that if I take the magnitude of x tilde in this case, right, it's going to be the magnitude of x divided by the magnitude of x squared, which is going to be, okay, 1 over the magnitude of x. So maybe that's giving some clue as to why you would expect a scaling by this magnitude of x to show up there, okay? But let's actually check that this works, okay? So to check that g of xy actually equals to 0 for x living on the interior and y living on the boundary, okay? What do we need to show, okay, that the magnitude of their arguments is going to be the same, okay? So that the magnitude of x minus y is equal to the magnitude of x times the magnitude of x tilde minus y for x being in the ball, okay? X tilde, of course, defined as we said it was, okay? And y is going to have magnitude 1 because y lives on the boundary in this case, okay? So let's just check that this all works out, okay? So in order to do that, I'm going to go ahead and square this here. I get x squared, x tilde minus y squared. I'm going to go ahead and plug in and then distribute my my x squared term here and my x tilde term here. So I get x divided by magnitude of x minus magnitude of x times y. But remember, y has magnitude 1, so we're probably going to use that later. I'll multiply this through by y squared because y, again, it just has magnitude 1. Just so I can see what's going on here. So if I sorry, no, I didn't do that. I'm just gonna square this whole thing out now, right? So if I square this whole thing out, and sorry, I'm gonna flip the order of this. Then I have the magnitude of y squared, the magnitude of x squared. I'm going to distribute through the interior terms here, right? So this is this times this twice, and then plus y, which would just be, sorry, plus 1, which would be this term here squared, which is going to be magnitude of x squared over magnitude of x squared, which would be 1, okay? And then because the magnitude of y equals 1, then, right, we then have that this is equal to the magnitude of x minus y squared, right? Because this is just going to be 1, right? And then this is just going to be, and you could write this as magnitude of y squared. Okay. All right. So everything matches up as we would hope, okay? And so because the arguments of these are the same on the boundary, then we should expect the values to be the same on the boundary. And so that means that they should cancel out, and therefore g of xy equals 0, okay, in this case, okay? So that's that's one big part of the Green's function, right? The other part, remember, is making sure that we only have one singularity living inside of our domain, okay? That's why with method of images, you always reflect outwards from the domain in order to put your singularities out there, okay? So the last thing we check then is the Laplacian of G, okay, is equal to delta of x minus y. And this is true essentially since the Laplacian minus Laplacian of our fundamental solution, okay, is equal to delta of x minus y, okay, essentially on x and y in u, right? But minus the Laplacian of phi of x tilde minus y is equal to 0, okay? Because x tilde is not in the closure of u, okay? Whereas y is in u in this case, okay? So we never meet any of the singularities by taking x values inside of u in that case, okay? So all of this taken together, right, means that G is the Green's function for the unit ball, okay? G of xy is the Green's function, okay, for the unit ball here, okay, with G of xy equal to 0 when y has magnitude 1 and x lives in the ball here. Okay. So those are our two kind of primary domains that we'll talk about for method of images, okay? Any questions about what we just did there?
Is there a way to define method of images, like recursively or something, where you zero out portions of your maybe geometrically weird boundary and then do that iteratively to zero out more portions while making sure the previous ones are still zeroed out?
If you have a clean enough boundary that you have some hope of doing that, right? So, and in fact, that's what you'll kind of do on the homework. There's also plenty of prelim problems like that. But yeah, if I think what I'm going to draw is something that's not that weird, right? If you just have the unit disk, right? But then essentially you just take the upper quarter of it, right? The idea here is that first of all, you just have your phi here, right? But I could reflect outside to here, right? And so that would mean I would take, an x tilde that's essentially x1 and minus x2. Over here, I would have an x hat that's like, would be minus x1 and x2, okay? And then out here, right, you have some, I don't know, I have to call it xb or something like that. And that would be your x divided by x squared here. But then in addition to that, right, you need the image points that you get by applying this transformation and this transformation. The image points that you get from applying this transformation and this transformation in order to cancel things out. So as long as your domain, right, is made up of, the boundary of your domain is the intersection of boundaries that you have a nice, accessible image point kind of transformation for, then you can do that. The alternative is to build a Green's function using eigen functions essentially for your domain. And sometimes you just have to find those numerically, and then you can construct your Green's function from that. But again, yeah, the power of the technique is that you only have to do that once for a domain, and then you can apply it to different problems. Yeah, that's a good question. Other questions? I guess, yeah, I mean, and another thing that you might think of is like the situation where, let's say you had a strip or something like that in space here, right? I think the iterative problem then in that case is to take the image point out here, right? But then you have to take an image point that's at a proper position that's going to, cancel out the effect on this boundary. But then by introducing that image solution, you're then gonna change the boundary value at this boundary. So you have to step further out here. So then you'll get infinite expansions in that case. So that's another thing that can happen. Okay. That's method of images. Yeah, you'll homework 7, you'll have an opportunity to practice that technique. But typically you start with these sort of atomic cases, and then build up from that.